Hi, I'm Dan DeBlasio. I'm an assistant teaching professor here at the School of Computer Science, specifically in the Computational Biology Department. As a teaching track faculty, I really like to introduce what I do by starting with my teaching philosophy. And really, my teaching philosophy comes down to trying to teach our students how computer science can integrate with other scientific disciplines. Specifically, since I'm in the Computational Biology Department, we're talking about integrating computer science and biology. And it's sort of a symbiotic relationship here. One of the main things that I try and teach people is that biology can provide very interesting algorithmic questions, right? What it can do is, given the data that they have, it can lead to interesting sort of theoretical computer science problems. If we think about protein interaction networks, right, those can be thought of as social networks. And now we need to do something interesting to figure out correlations there, right? Same thing with building trees to figure out relationships between species. At the same time, when we do solve those problems, not only is it just solving the computer science problem, but now we can provide insights to those biologists to make further discoveries downstream, right? So they can have extra things that they want to test based on the insights that we provide to them. And this isn't just biology, right? This could be chemistry or engineering as well. But within our department, usually it's in the context of biology. And I use that idea not only in my teaching, but also in the work that we do in my group. So in my group, what we're trying to do is build an automated scientist, right? So at the end of the day, what we want to do is allow biologists to do their job better, right? So biology, because we're getting really good at sort of doing experiments and collecting a bunch of data, because we have a lot of data, now we have to use a bunch of computational tools to actually do the analysis for us. No longer can we do it on our own. So as modern science becomes increasingly computational, people are relying on these tools that are developed to solve the problems. But a lot of the tools that are being used are computationally inefficient. They're sort of hard to use, and they have a bunch of tunable parameters, right? So this is an example of one tool that's used in the field, and you can see that it has quite a few parameters that can change based on any given input. And you might want to change them based on what you're looking at. But because there's so many tunable parameters, and these tools were built by some computer scientist or some computer science graduate student, most likely, it might not be intuitive as to exactly how to set each one for your new input. So that leads a lot of people to go either look online for these answers on how to set these different parameters, and they might come up with many, many different solutions or answers, or none at all. But what happens is, because of this frustration, a lot of people just use the default parameter settings, right? A tool is going to come with whatever it does if you just pass it the input and don't tell it anything else. And that works a lot of time. These defaults are meant to work on average, right? So they work on the average input. But the most interesting inputs, right, the ones that the, say, biologist is really interested in, is not average, right? So here's an example. You don't really need to know what the data is, but it's multiple sequence alignment. And what's supposed to be happening here is those red characters are supposed to be aligned up with each other. And we can see that the default parameter settings don't provide the right alignment. But there is some setting of the parameters that does, right? So it's not that the tool always gets it wrong, it's that the parameter settings are leading us astray. And this isn't just a problem in computational biology. Here's a couple examples of other domains within computer science where they're having the same problem. So what we want to do is, since all of these tools can be greatly impacted by the choice of parameter, and the most interesting inputs are not average, we want to make sure, can we remove parameter choice as a source of error in downstream analysis? So can we make it sure that that biologist, when they use the tool, isn't going to cause a downstream issue based on the parameters that they chose? So what would be great is if we had, this is our scenario, we have our input and some scientific application. It'd be great if we had some all-knowing oracle that can look at the input and tell us, this is the parameter vector you should use, right? This is the settings for that tool that can provide the best output. But since that oracle doesn't actually exist, we came up with an advising framework that we call parameter advising that can get towards what that oracle would do. So a parameter advisor takes as input the same data that would go into our original scientific application. It uses a collection of parameter vectors. So these are sets of settings for each of these parameters. And it uses that set to create a set of candidate solutions, right? So it uses each parameter vector to produce a candidate solution. Once we have all of those candidate solutions, we can assign each one an accuracy, except that we can't normally measure accuracy directly because accuracy is based on some ground truth. And if we knew the ground truth, then we wouldn't need to estimate it, right? But once we've assigned an estimated accuracy to each solution, our advisor can pick the best one and return it to the user. What's really cool is to the end user, it looks like some new scientific tool that solves the same problem they were looking to solve, but without any tunable parameters, right? It's doing all this in the background. At the same time, to come up with a new estimator for a new problem, all we need to do is define the advisor set and the advisor estimator. And this is where the computer science comes in, right? The advisor set needs to be small and it needs to be representative. It needs to be small enough because we don't want to run the application too many times, right? We don't want to use too many computational resources. And it needs to be representative because we need to have at least one parameter vector that works for every input. It turns out this problem is NP complete, which led us to finding an approximation algorithm. So this biologically inspired problem leads to something very interesting as a computer scientist. At the same time, we also need an advisor estimator, right? An accuracy estimator that's efficient because we need to run it for every input. And it needs to be really good at ranking solutions. Once again, we've proposed a couple different solutions here, one using an integer linear program, one using deep learning, and a couple other solutions as well, right? So again, the biological problem has inspired a really interesting computer science problem. We're continuing this work applying parameter advising to other domains as well as some other new questions. But the idea comes back to using this concept of taking ideas from biology into this computer science space and then sending it back. Can we be inspired in computer science by other domains, solve a really cool problem that's interesting not just to the biologists, but to the computer scientists as well, and then give something back?